presentation this evening rather than our regular lecture. While we're going through the presentation, I encourage you to pause the presentation and try to work out the solutions to the problems yourselves before you watch me write in the solution. At the very least, you can try to at least get a start on the problem, writing down some of the key pieces of information, as well as maybe the equations that might apply in that particular circumstance. I'm going to apologize in advance for the sort of off-the-cuff delivery here. I don't have a script. I'm just going to present this as I would if I'm talking in a lecture. So please bear with me, and I hope this is a satisfactory substitute for our lecture. Enjoy. So this evening we don't have a lecture, but this is the week that we're on. You guys will actually have a quiz on problem set number 2 next week. So hopefully you guys are working diligently on getting those problem set questions answered and working well with your groups to make that happen. From the formula sheet, we're going to be using F equals mg tonight, as well as density equations, and basically most of the stuff from the fluids section. So hydrostatic pressure, buoyant force, surface tension, all the way down to contact angle potentially. Okay, nothing really from the back of the formula sheet except for possibly some of the constants and conversions over here. Okay, so let's get started. Here's a picture of a giraffe, and on the right is a picture of a sphygmomanometer, which is the word we use for a blood pressure recording device. And a blood pressure recording device measures both the systolic and diastolic pressure. Systolic is the pressure measured when your heart is actually squeezing the blood through your body, and diastolic is when the heart is relaxing. So that's why the systolic pressure is higher than the diastolic pressure. In humans, a blood pressure of 120 over 80 is pretty typical, and that measurement is represented as millimeters of mercury. So when we're talking about pressure, remember, we can think of pressure as the amount of force produced by a column of water or fluid, and in this case we measured the number of millimeters of mercury, which would cause a specific pressure difference from the top of the column of fluid to the bottom, and that's the pressure that we're measuring in when we perform those blood pressure measurements. If a giraffe's blood pressure at its head 6 meters up from the ground is 210 over 150, what is the blood pressure at the bottom of the neck 4 meters above the ground? So they're giving us the pressure at the head up here, and they're asking us what is the pressure down at the base of the neck. And you'll notice that this height difference is 2 meters, which is just a little bit taller than the average human. So a giraffe's neck is just as long as your entire body, so you can expect a similar pressure drop between the top of your head and the bottom of your feet. Where I would encourage you to pause the presentation and try to work out the solution yourself, and then I'll go ahead and work out the solution for you. Okay, so here we go. I'm going to work out the solution. So we're looking specifically at the max gauge pressure, which is 210 millimeters of mercury, and we want to know, so at this point right here, we have a pressure of 210 millimeters of mercury, and what we want to know is what is the pressure at this point here. Okay, that's what we're asking. And so because there's a height difference, what we're looking at here is the pressure difference that comes from the hydrostatic pressure equation. So delta P is equal to rho G delta H. In this case, we need to use for the density of blood. So the density of blood is actually pretty close to the density of water, which is 1,000 kilograms per meter cubed. So we can use that. And so then we can just start plugging things into our equation. So let's take a look. We've got the density we know is 10 to the 3 kilograms per cubic meter. G we know is about 10 meters per second squared. And the change in height is 2 meters. Okay, and so then the key here is that we've got to convert this into appropriate units so that we can figure out what this is in millimeters of mercury, because this pressure difference done in SI units is going to give us, well, 1,000 times 10 times 2, that gives us 20,000. And because all of these are SI units, that's 20,000 pascals. Okay, and so then in order to convert that into millimeters of mercury, one thing that we can do is we can just take a look at how many pascals are equivalent to millimeters of mercury and make that conversion. So 10 to the power of 5, okay, is 100,000, like that. Okay, so what we can do is we can say, we can multiply this by 760 millimeters of mercury for every 100,000 pascals. The pascals will cancel out, and 20,000 goes into 100,000 5 times. And so then we're looking at 760 millimeters of mercury divided by 5, which works out to approximately 150 millimeters of mercury. So that might lead you to answer B. However, it's important to recognize that this is a change in pressure, and so if the pressure up here is 210 millimeters of mercury, the pressure down here, because we're going to a deeper point, is going to be a higher pressure. So the absolute pressure at that point is going to be the 210 millimeters of mercury that we had above, plus the difference in pressure, which is 150, giving us a total of 360 millimeters of mercury. So your answer should be C. So that's the end of that question, and this is where I would pause and see if there's any questions from the audience. Obviously we can't do that at this stage, so if you do have questions about how that works, please feel free to ask me at our next lecture, or send an email to myself or Dusty, and we can try to address some of those concerns. Of blood pressure in humans. So systolic is the top number, like, so the 120 over 80 refers to 120 over 80, and ideal blood pressure for humans is a systolic pressure that's 120 or below, and a diastolic pressure that's somewhere between 60 and 80. If your blood pressure is too low, then you can suffer from dizzy spells, and if, for example, you might not be getting sufficient blood flow to your brain. And if your blood pressure is too high, then you're suffering from what's called hypertension, and this can lead to cardiac failure later in life. So you might get a heart attack, or you might have other health-related issues if you live a long time with high blood pressure. So that's an important thing to understand. You should go to the doctor and make sure that your blood pressure is in the reasonable range. It might also be useful for you to go check it out on a regular basis at, like, Shoppers Drug Mart or something. They have those automated blood pressure sensors, so you can go and put your arm in and get it checked out. What's interesting is that a tall animal such as a giraffe needs to overcome significant hydrostatic pressures because they're so tall. This means that they need a much stronger heart that produces way more pressure. And so you saw in the example with the giraffe, it was significantly higher blood pressures than what we're dealing with. Okay. There's a just-in-time quiz question that asks which material property most directly determines if an object will be net buoyant or if it will float in a given fluid. And so this particular cohort actually did quite well in answering that. 82% correctly identified the density as the property which determines whether or not something will float. So if you put an object in a fluid and it is more dense than the fluid, then it will sink, and if it's less dense than the fluid, then it will float. Fluid that is displaced by that object. Okay, so you guys answered 79.8% correct back in 2016. That was 78.9%. So almost identical results on that question, which I find quite interesting. Now, we're going to be talking about fluids and buoyancy in fluids from here on in this lecture, so let's take a look at what we've got. So, from the course notes, you've got this equation 2.4. The buoyant force is equal to the density of the fluid times the volume of the object times g. And so we can imagine just a container with a fluid in it. Okay, and here is an object in that fluid. Now, at all times, an object will be experiencing the force of gravity on it. So if I draw an arrow representing the force of gravity is equal to mg. But it's also equal to the density of the object multiplied by the volume of the object times g. Because remember, the density is equal to mass over volume, which implies that mass is equal to density times volume. So that's the conversion that we're using here. Mass is equal to the density of the object times the volume of the object. Now we'll take a look at the buoyant force acting on the object, and we'll see that there are some similarities and there are some differences. The buoyant force is equal to the density of the fluid times the volume of the object times g. So the buoyant force and the force of gravity have some similarities. They both are based on the volume of the object times g. But the buoyant force depends on the density of the fluid, while the force of gravity depends on the density of the object. And so this is where the density is what determines whether something will sink or float. If the density of the fluid is greater, then the buoyant force is going to be greater, and the object will tend to move upwards. If the density of the object is greater, then the force of gravity will win out, and the object will tend to sink down towards the bottom of the container. We can also do that free body diagram one more time and just realize that the force of gravity is a vector and the buoyant force is also a vector but pointing in opposite directions. So the net force acting on the object is going to be the vector sum of the buoyant force and the gravitational force acting on that object. Okay? And depending on which one of these forces is greater, the net force could be upwards or downwards. Okay? Now, taking a look at a quick application of this, you may find it interesting that your brain is supported entirely by the brain stem, and this is only possible because the brain is actually sitting in what's called the cerebral spinal fluid, and this creates a fairly significant buoyant force on the brain, which decreases the apparent weight of the brain. So the apparent weight is basically the weight of an object after buoyant forces have been accounted for. Taken into account. So without those buoyant forces acting on the brain, your brainstem would not be able to support your brain, because your brain is actually quite heavy. But when we do account for those buoyant forces, we can see that the apparent weight of the brain is only about half of a Newton, and so therefore it's quite reasonable to expect the brainstem to support that kind of a weight. There's also this example in the notes talking about an iceberg and how it floats in water, and perhaps you've heard before that most of an iceberg is actually submerged, but you may not have known how much of it is submerged. And so that's what this calculation here shows. We're using the density of ice compared to the density of the fluid, and it turns out that the density of the ice is 89% of the density of water, and therefore 89% of the iceberg is submerged. So 89% of the volume of the iceberg is submerged, with the remaining 11% showing on top of the water. And you know, this is actually, if you think about it, quite amazing. There really is a huge amount of ice underneath the water for every iceberg that we see. And essentially the Galilean thermometer is something that uses the concepts of buoyancy, relative buoyancy, whether things float or sink, to determine the temperature of the environment. Because one of the things that's important to understand is that the density of fluids, the density of water in particular, does change with a change in temperature, and this Galilean thermometer takes advantage of that. So let's move on for now, and I'll talk about that next week. Now, here's another clicker question that we would do. So at this point, pause and see if you can work out the solution yourself. And now I'll take up the answer. Okay, so in this question, fish can regulate their density by inflating or deflating their swim bladders. At a particular moment in time, Nemo and his dad have the same density, slightly more than the ocean water, and they are thus slowly sinking. Which of the two is experiencing a larger force of buoyancy, and which has a larger apparent weight? So the key here is that it's asking us about the larger force of buoyancy and the larger apparent weight. So let's look at the buoyant forces that are acting on these two fish. So the buoyant force here is going to be the density of the fluid, so the water, times the volume of Nemo, times gravity. And the buoyant force on the dad is going to be the density of the fluid times the volume of the dad times g. So the only difference in these two expressions is the volume of Nemo versus the volume of the dad. The dad is bigger, so we know that the volume of the dad is greater than the volume of Nemo, and therefore the buoyant force for the father is going to be greater than the buoyant force for Nemo. So the buoyant force for the father is greater than the buoyant force for Nemo. So buoyant force, Nemo is not greater than the dad, Nemo is not equal to the dad, so it's either got to be C or E. And then the next thing that we look at is which has the larger apparent weight. So if we look at the expression for apparent weight, remember that apparent weight is equal to the force of gravity minus the buoyant force. I should say buoyant force. So force of gravity, remember, for any object can be written as the density of the object times the volume of the object times g. So in this case, we've got the density of the object times the volume of the object times g minus the buoyant force, which is the density of the fluid times the volume of the object times g. And so these are important expressions because you'll notice that there's a common factor of the volume of the object and G, and then it's the density of the object minus the density of the fluid. Now, this term is going to be constant because they both have the same density. Okay, so Nemo and his dad have the same density. So in this particular question, this is the same for both of the fish. So again, it comes down to the volume of the object. Which one has the greater volume? The dad does. So because the volume of the dad is greater than the volume of Nemo, we can conclude that the apparent weight of the dad is going to be greater than the apparent weight of Nemo. So looking at our results, the apparent weight of the dad is greater than Nemo. So this is the right answer, and that's the wrong answer. So our answer is C. Pause there so you can pause the video if you need to look over that solution, and then we'll move on. Floating in fluids. Here we have some water, and we have a fish, and we have an iceberg, and we have a marble. Okay, all three objects experience a gravitational force downwards. In other words, their actual weight is equal to the force of gravity, which is equal to m times g, and they all experience a buoyant force upwards. Okay, so the buoyant force is the mass of the water that is displaced, which is equal to the density of the fluid times the volume of the object. Okay, so that's equal to the mass of water. And so here's an important concept. When an object sinks, it can only displace its own volume. It can never displace a volume greater than the volume of the object. So here's a tricky question. What would happen to the water line if the marble was taken off the bottom of the pond or whatever and placed on top of the iceberg? Okay, now this is a fairly deep question, and you might have some guesses or intuition right off the bat, but we're going to talk about this in a little bit more detail, so I'm not going to tell you the answer just yet. So let's take a look at some important features about a couple different objects. Okay, so here's an object which, so we'll start with object 1. For object 1, it is buoyant, so it is able to float on the top of fluid, and it has a buoyant force which is equal to the density of the fluid times the volume of that's been displaced. Okay, so just the volume that's been displaced, because part of that object is not displacing water. Okay, so the top part here is not displacing any fluid, and therefore it does not get included in the buoyant force calculation. This part here gives us a force of gravity. The force of gravity is equal to the density of the object times the volume of the object times g. And because the object is floating, what we know is that the net force is equal to 0 because it's not moving up or down anywhere. And therefore, the force of gravity is equal to the buoyant force. So we can write this equation down. The density of the object times the volume of the object times g is equal to the density of the fluid times the volume that's been displaced times g. Now let's look at object 2. Okay, for object 2, we have the force of gravity, which is again the density of the object times the volume of the object times g, and we have a buoyant force. Now this time the object is completely submerged, so we are going to use the density of the fluid times the volume that's been displaced times g, but the volume that's been displaced is actually the volume of the object. Okay, and for object 2, it has an apparent weight because the buoyant force and the force of gravity are not balanced because this thing sinks to the bottom. So the apparent weight is going to be equal to the force of gravity minus the buoyant force. So in other words, the density of the object times the volume of the object times g minus the buoyant force, so the density of the fluid times the volume of the object times g. So you may recognize this from a problem that we did earlier. Again, we can factor out a couple things here. The volume of the object times g, and that leaves us with the density of the object minus the density of the fluid. So because the density of the object is greater than the density of the fluid, this is a positive value, and it has a positive apparent weight, which makes it sink to the bottom. So when you're looking at an object that's submerged in water, whether it's partially submerged or completely submerged, these are the equations that you can sort of write down without even really having to think about it, because they're going to be the same each time. Okay? Now, one of which contains a plastic ball, and the two beakers are then filled with water to the exact same water line. Which beaker with all its contents weighs more, or are they of equal weight? So at this point, I'll pause, let you try to work it out, pause the video or presentation if you would like, and now I'll present the solution. So the key concept here is to look at what's going on with this ball here. Okay, so if we look at the ball, it has a force of gravity acting on it, and it has a buoyant force acting on it. And as we just saw from the last slide, we know that the force of gravity is equal to the buoyant force in this particular case because it's floating on the top of the water. Now remember that the buoyant force is going to be equal to the density of the fluid times the volume that's been displaced times g, and that is going to be equal to the mass of the water that's been displaced. Times g. So those two things give us the mass of the water. The force of gravity is going to be equal to the mass of the ball times g. Now, since the buoyant force is equal to the force of gravity, we know that the mass of the ball is equal to the mass of the water that's been displaced. So taking these two equations and equating them to each other, the water that's been displaced here weighs exactly the same. So here, this water has been displaced by the ball, and this water here weighs exactly the same as the entire ball. Therefore, the contents of the two beakers are of equal weight because the only thing that's left is the same volume of water. So both systems weigh the same, not weight the same, but weigh the same. So that may be an interesting conclusion that you might not have thought of. Now the next question is, of course, what if the ball was on the bottom? If the ball were on the bottom, then we know that the density of the ball would be greater than the density of the water that surrounds it, and therefore it would be beaker B that weighs more. See that has a very high salt content, and therefore the density of the water is significantly higher than the density of a human. Now, the question here is, what percent of your body's volume extends above the waterline when you are swimming in the Dead Sea? And so again, pause the presentation if you would like and try to work this question out on your own. And now I'll present the solution. So in order to solve this, all you really need to do is take a look in the notes at the iceberg example. Okay, and we can derive all the equations again if we want, but the end result is that we can figure out that the volume that is in the water divided by the total volume works out to the density of the human divided by the density of the sea. And so the density of the human is 1.0 kilograms per liter. The density of the sea is 1.25 kilograms per liter. And that works out to a fraction of 4/5, which is 80%. So the volume of your body that would be in the water is 80%, which means that 20% is out of the water. And so that's how we solve that. 20% of your body would be floating above the water. And if we do a quick mental check, that's kind of similar to the iceberg example where 11% of the iceberg is floating out of the water. Okay. Moving on now, picture yourself on a small boat. So this is like the marble on the iceberg question. Picture yourself on a small boat in a large fish tank with an empty bucket and a large sack of sand. Okay, so this is kind of a question where we're going to imagine a pond. It's got a water level here, and here you are in a boat. Okay, your boat has a sail. For some reason, this is you, and you have an empty bucket, which is almost as big as you for some reason, and you have a large sack of sand. So you need to think about those three things, okay? And here's the water level on the tank. Okay, and we're going to imagine that this tank is, quite small, so that if there were any changes, they would be large enough that we could measure a change in water level on the side of the tank. So the question is, what happens to the water level on the tank walls after you reach down and fill the bucket of water and place it full in the boat? So pause the presentation, take a moment to think about this, and then try to answer it yourself. And now I'll take up the solution. So the idea here is if you've got an empty bucket here and you reach down and you fill it with water, then you're going to take a volume of water out of the pond. Okay, so this has some volume here, which equates to some mass of water, and that mass of water is going to be equal when you put it onto the boat, and so the boat is going to sink down and then displace an equivalent mass of water. So it doesn't really matter where the water is located. Okay, it is going to have the same volume whether it's in the water itself or whether it's on the boat. So nothing happens to the water level, it stays exactly the same. Okay. So again, take a moment, think about this, and now I'll take up the solution. So many of you might be tempted to say nothing. Again, the water level stays the same, but there's actually a pretty key feature here that makes that answer not true. So remember or recognize that the density of the sand must be greater than the density of the water because it sinks to the bottom. Okay, and so then we want to look at what's going on with the sand when it's in the two different locations. Okay, so here's the water level, here's the boat, here's the sack of sand. Okay, and then the sand goes and it lands in the water, and then it's down here. So when it's in the water, the volume that is displaced by the sand is exactly equal to the volume of the sand, because it can't be anything different than that. Okay? But when it's in the boat, okay, the sand is floating. Therefore, the volume that's displaced is equivalent, it represents a volume of water with a mass that's equal to the mass of the sand. Because that's what happens when something floats. The mass of the object is exactly equal to the mass of the fluid that's being displaced. Okay, so that's the key here. The mass of the sand is going to be equal to the mass of the water that's being displaced. Okay? Now, what we know is that density is equal to mass over volume, and therefore volume is equal to mass over density. And so the volume of water that's being displaced is equal to the mass of water. Let me see if I do this right. The mass of water divided by the density of the water. Okay. And because the mass of the water is less than the mass of the sand, let me make sure that I get this right. Yeah. Okay, so the mass of the water that's being displaced is equal to the mass, or the volume of the water that's being displaced is equal to the mass of the water divided by the density of the water. But in terms of the volume of sand, okay, so the volume of the sand is equal to the mass of the sand divided by the density of the sand. So this is the volume that it displaces when it's in the boat, and this is the volume that it displaces when it's on the bottom of the tank. If we look at being in the boat, the mass of the water that's displaced is equal to the mass of the sand. But the density of the water is less than the density of the sand. Therefore, the volume of the water that's displaced is greater than the volume of the sand. So the sand displaces more water when it's in the boat than when it's at the bottom of the tank. So if you take the sand and you throw it off the boat and it lands on the bottom, it's now going to displace less water, and the water level on the tank walls is going to go down. Okay? And this might be counterintuitive, or it might be hard to wrap your head around. I'm going to do a demo next week where I have kind of a makeshift boat with some makeshift sand in it, and I'll show you exactly what happens to the water level when I take the quote-unquote sand from the boat and put it in the bottom of the tank. Okay, so I'll actually show you that demonstration next week, and hopefully you'll believe me then. Laboratory scale to measure a tiny amount of sodium phosphate powder. The scale measures 1.2345 grams. Were the atmosphere of the Earth removed, what would the scale now measure? So the idea here is that the atmosphere is air, which is a fluid, and therefore there is some small buoyant force due to the atmosphere, and therefore when you remove the atmosphere, you remove the buoyant force, and the apparent weight of the object goes up. So you would expect it to be slightly more than 1.245 grams, but how much more is pretty minuscule. It's not really that important. Okay. All right, and here's another one. So a toddler lets go of a plastic bath toy at the bottom of the tub. The toy slowly rises to the water's surface. At a particular moment in time, the toy is at position 1, 40 centimeters below the surface of the water. So point 1 is here, and this is 40 centimeters. And position 2, at another moment, the toy is at position 2, which is 10 centimeters below. 10 centimeters. Which of the following statements is most true? Note all pressures listed below refer to gauge pressures. So what's important to recognize is that the buoyant force is dependent on the density of the fluid, based on the density of the fluid and the density of the object, and neither of those two things are changing, so we would expect the buoyant force to be exactly equal at both positions. So that means that A can't be right, and B can't be right, and E can't be right, so it's either C or D. And then we want to find out which one has a greater pressure, and so the answer then is that when we are looking at a pressure difference here, the change in pressure from the top here to here is based on hydrostatic pressure, so that's rho g delta H. The change in height is 10 centimeters versus 40 centimeters, so the depth for position 1 is 4 times greater than the depth for position 2, and therefore the gauge pressure will be 4 times greater. So D is our answer. Okay. Ball has a higher apparent weight. And the answer to this one is that we simply don't have enough information because we haven't been told the densities of the rubber and the bone. So you might try to make a guess, but it's actually impossible to tell in this particular situation. Okay. That is the end of the discussion on fluids and buoyancy, and now we'll have a conversation about surface tension. And so when we're looking at surface tension, this is the section of the notes that's interesting to us. And so what we have here is an equation that gives us the surface tension is related to the surface energy divided by the surface area, and so we get a couple equations from this. The force on a linear section is equal to the surface tension times the length of that section, and the amount of energy that's stored in a particular surface is equal to the surface tension multiplied by the area. And from that, if we have a change in area, then the change in the energy would be equal to the surface tension times the change in area. Or you could have a change in surface tension as well, so the change in energy could be equal to the change in surface tension multiplied by the area. Okay, so this symbol here represents surface tension, and in this case E is representing surface energy. Okay, now what we can look at is this example from the notes again. So it's pictured in an upright position, but we're actually imagining this horizontal or flat. so that this is not a gravitational force but an applied force. So surface tension forces will try to minimize the surface area of any fluid film. And so if we have a wire with a length L, then there's going to be surface tension forces acting all along the length of the wire. And the longer the wire is, the greater the force will be, because there's a greater length to act upon it. And so you have to apply some applied force to keep that wire in the same location. If you apply a force which is greater than the surface tension forces, then you can actually change the size of the fluid film and increase the energy as a result. So one other thing that's interesting to note here is that the energy is right here, so it is linear with the extension. So as we make it longer, the energy increases in a linear fashion. So like this. And that's different than energy storage in elastic materials. You remember from a few weeks ago we derived that relationship and it turned out to be quadratic. So that's an important factor, because what it means is that as we're applying a force, it doesn't get any harder to keep stretching that thin fluid film. Imagine that you are working with an elastic and you're stretching it, and as you stretch it further and further, it gets harder and harder to stretch. That's why the amount of energy stored becomes quadratic. But for a thin fluid film, imagine blowing bubbles, like soap bubbles. As you make the bubbles larger and larger, it doesn't get any more difficult to make them bigger. They just continue to become enlarged. So that's this linear relationship of energy storage with. Okay, so I'm not sure what happened there, but hopefully it hasn't glitched too much. Okay, so another thing that we can look at then is various surface tensions for different fluids. And what's interesting is that if you look at soapy water versus just regular water, the surface tension actually decreases by about half. And so some organisms can actually take advantage of this sort of thing to propel themselves. So here's a concept question. A couple of drops of soap are added to the 10 centimeter by 10 centimeter surface of water in a container, such that the soapy water now thinly coats the entire surface. How much energy is released to the environment in the process? So here you would want to try to work it out yourself, pause the presentation, and then we'll take it out. So here we go. If we look at water and air, surface tension is 0.072, comparing that to soapy water and air, which is 0.03. So the change in surface tension is 0.04 newtons per meter squared. Should be an area, yeah. Or no, it shouldn't, sorry. Okay, now the area here is 10 centimeters by 10 centimeters, so you actually have to do a unit conversion because we want to work in meters. So 10 centimeters is 0.1 meters squared, which works out to 0.01 meters squared. So make sure that you convert units before you square them, because once you start squaring things, it can become complicated. Now, we have a couple equations here. Surface tension is equal to energy over area, and that's equal to force over length. We're looking for energy, so the energy in a surface is equal to the surface energy multiplied by the area of the surface. In this case, It's this the surface tension, which is changing. So the change in surface energy will be equal to the change in surface tension multiplied by the area. So in this case, the change in surface tension is 0.04 newtons per meter, multiplied by the area, which we already worked out was 0.01. So that's going to give us 4 times 10 to the minus 4, and energy units are joules. We've done everything with SI units, so we know that we're going to get joules as a result. And so we get 4 times 10 to the negative 4 joules. Okay. Alternatively, you could work out the amount of energy in the surface with both values and then do a subtraction if you wanted, but I find this way to be a little bit more efficient. Such that the surface shape of the water is unchanged. So the reason we identify this is because we are not going to worry, don't worry about meniscus effects. Okay, so you may have read about meniscus effects in the reading. We're not going to worry about that for this question. Given enough time for the water to cool a bit behind the boat, what happens to the boat? So the key concept here is that the surface tension in warm water at 100 degrees compared to, let's say, 20 or 0 degrees Celsius is an increase. So there's an increase in surface tension, increasing surface tension as we cool water down. So if I have a boat, you can tell it's a boat because it has a sail. If this is the front of the boat here, so here's the front of the boat, we are going to place an ice cube behind the boat. So here's the cube of ice. Okay. The surface tension for the warm water, so it's going to be warm here, which means it's going to be relatively low surface tension. And back here it's going to be cold, which means it's going to be relatively high surface tension. And a higher surface tension means that it wants to pull on the object, and therefore we are going to get a net force towards the cold water, and the boat will begin moving slowly backwards, which is quite an interesting result. Okay. Moving on then, talking about soap bubbles and bubbles in general. We can talk about this transmural pressure difference. So basically, if we have a bubble like this, okay, there's a pressure inside the bubble and there's a pressure on the outside of the bubble, and that pressure difference is called the transmural pressure. Okay. Now the pressure inside the bubble has to be bigger than the pressure outside the bubble, otherwise the bubble would just collapse, because surface tension is trying to minimize the surface area, and so it's always pulling the bubble to be as small as possible. And so that's how we actually determine how large a bubble is because we've got the surface tension forces trying to minimize the size of the bubble, and we've got this pressure difference between the inner pressure in the bubble and the pressure outside that's then pushing back against that. Okay, and so then the important thing to also make note of is that this factor is due to the fact that there are two surfaces in an empty bubble, and it also has to do with the fact that the bubble we're talking about is a sphere. Okay, other conditions will lead to a different factor here, but we'll always make sure that it's clear what that factor should be. Okay, so don't worry if you don't know why that's a 4. We'll make sure that you know what it is if you need to do a calculation with it. As they float about, which bubbles have a larger internal pressure. And so if we take a look at that equation, the transmural pressure difference is equal to 4 times the surface tension divided by the radius. So the pressure difference is inversely proportional to the radius. So in other words, as the radius increases, the change in pressure decreases. So the largest change in pressure is going to happen for the smallest bubbles. And so that's why that is the correct answer. Okay? Okay, so then that leads us directly into this concept question. In the following situation, there are 3 soap bubbles connected by a series of tubes. The red dividers are removed. What happens next? And there's a series of results there. So pause the presentation and think about what's going on with the pressure inside the bubbles and how that would impact the end result. Okay, and now what we'll do is we'll take it up. So we just realized that the pressure difference is inversely proportional with the radius. So the smaller the bubble, the greater the pressure difference, and therefore the pressure in bubble 2 is greater than the pressure in bubble 1, which is greater than the pressure in bubble 3. So when these dividers are removed, the higher pressure in 2 and 1 will cause the air to rush into bubble 3. And so the largest bubble will get bigger. And this is an important issue in neonatal respiratory distress syndrome. So basically what's going on here is our lungs have a mechanism for regulating the surface tension on the outside of our alveoli, so that when there's differences in the sizes of the alveoli, they don't all cause the higher pressure in the smaller alveoli doesn't cause all the air to rush into the larger alveoli. And so sometimes that doesn't work out, and that's when we get this neonatal distress syndrome. And so basically the previous example showed exactly what goes on. The smaller bubble will have a larger pressure. The pressure in 2 is greater than the pressure in 1, and the regulatory systems aren't functioning normally, and so the air from this alveoli rushes out and fills up this alveoli. And there's a reason why our lungs are designed with many small alveoli, is because we need more surface area. If we had just one large alveoli in our lungs, we wouldn't have enough surface area to effectively perform respiration, and therefore we wouldn't be able to breathe properly and get oxygen into our bloodstream. So we need to have many small alveoli to have lots of surface area. So many small alveoli leads to more surface area. Okay. So how do we get around this? Well, the trick is provided by nature, where lung surfactants with immensely reduced surface tension coat the alveoli in such a way that the smaller bubbles have a better coating of the surfactant and thus experience less surface tension, therefore permitting them to remain inflated as smaller bubbles under the same pressure. So if you think about that for a second, that's a pretty amazing mechanism that our body has available to us. We're able to actually regulate the surface tension on alveoli individually so that this collapse of the alveoli does not happen. Can you make a good argument for why the case of 2 inflated alveoli is preferable to the case of a single alveolus with the equivalent total volume? And so the answer is what we just talked about. One big alveolus doesn't give enough surface area. So that's a pretty important concept, and it's one of the main reasons why larger animals had to develop lungs in order to reach the sizes that they did. Okay, here's another concept question. If a pressure difference across a bubble membrane is kept constant and a surfactant reduces the surface tension by a factor of 2, what happens to the volume of the bubble? So go ahead and take a look at this and try to answer it. And now I'll write the solution. So the pressure difference across a bubble membrane is kept constant. So the change in pressure is constant. So this change in pressure is constant. And it's telling us that a surfactant reduces the surface tension. So the surface tension afterwards is half of the surface tension before. Now, because this is constant, because the pressure is constant, if this is a half of what it was before, then the radius also has to be a half of what it was before in order for this ratio to remain the same. Okay, because we already know that this is some constant. So this tells us that the radius afterwards is equal to 1/2 of the radius before. Now, the volume of the bubble is what we're interested in though. So remember that volume goes with radius cubed. Therefore, the volume of the bubble afterwards is equal to this 1/2 factor raised to the power of 3 times the volume of the bubble before. So that's going to be 1/8 of the volume before. So if you have a surfactant which reduces the surface tension by a factor of 2, then the volume of the bubble will be reduced by a factor of 8, which is a pretty significant difference. Okay? Next question. Does the health practitioner exert the greatest pressure from the outside through the mouth? So we're just asking in which of these steps is there the most effort that needs to be done. And as we know, the smaller the radius, the greater the pressure difference. And so we need to exert a much greater pressure through the inside of the mouth to blow up the bubble from this step to this step than we do from this step to during which step must a health practitioner exert the greatest pressure from outside the mouth. Yeah, so from this step to this step. Sorry, I was reading this as step 1 for a second. I read that. So this is the step that's the most important. And so this is the step where we're going to have the greatest pressure difference. And I'm going to stop our presentation right there. I encourage you to rewatch it. We're just over an hour here, so about 1/3 of the time of a regular lecture. But my expectation is that you've been stopping the presentation and trying to work out some of these things on your own in the meantime. So I hope that you've had some luck with that, and feel free to email with any questions if you have them. Take care.